I have been looking for somebody to do a presentation on 3D printing for at least 2 years with virtually no luck. My committee members know that, and there's been a lot of pain and agony over it. But so I went to a dinner gathering at a private home a few months ago, and somebody there was named Jane was there, and Jane's boyfriend was there too. And lo and behold, he does 3D printing for a living. So Jared Brown has a BS in plastics engineering technology and an associate's and science degree in computer assisted design, drafting, and tool design from Fair State University. He is also certified in 3 different CAD software applications. Brown has worked with 3D printing for tooling and prototyping in both the professional and educational settings for the last several years. So without further ado, Jared.
Can you hear me now? So this is an introduction to 3D printing basics. My name is Jared Brown. I'm currently an engineer at Flowrite and Hydron Limited. So without further ado, let's get into it. So 3D printing is also called additive manufacturing. Converse to that, we previously had a lot more to do with subtractive manufacturing. So there's a little bit of a difference between the two. Generally, 3D printing or additive manufacturing is the process of creating a physical object through the layering of materials. So throughout the use of a laser or extruder or other methods, layers are built up to create the shape and part that you desire. And then generally, there'll be some type of post-processing that will be a subtractive manufacturing process, which is subtractive manufacturing is also known as machining and subtracts the material from the object to create the desired geometry. So you can do some type of machining, lathing, 5-axis, 3-axis, to get the shape that you would desire out of your part. However, this is wasteful because basically you're taking all that excess material and then just throwing it away. So 3D printing actually saves on material cost. Moving on, I'm going to get into the types of additive manufacturing. So 7 types. You have your vat photopolymerization or vat polymerization, which is your SLA and DLP. We'll get into the acronyms a little bit later in the presentation, guys. But for now, this is kind of how people refer to them. So then you have sheet lamination, UAM, LOM, material jetting, which is just material jetting. It has components that it could be DOD or continuous. Powder bed fusion, which you can either do with polymers or you can do with metals. So the polymer side has SLS, the metal side has SLM, DLMS, and EBM. Next one is binder jetting, which is a weird one, which we'll get into because it kind of combines 2 things. Directed energy deposition, DED, which you can have regular DED, or you can have an upgraded version called EBAM. And then the hobbyist favorite, material extrusion. So material extrusion can be FDM or FFF. They're the same exact thing. FDM is a trademark from Stratasys, who makes certain 3D printers. But Triple F is the same thing as FDM. Moving forward, we have directed energy deposition. So we're just going to get started on this and flow down because some of these relate. So in directed energy deposition process, you're taking a laser, you either have powder feed or wire feed nozzles, like you're welding essentially, and you layer it up layer by layer to create your part. So it can either utilize wired or powdered materials. out of these nozzles to weld up. Like in welding, it's going to require an inert gas. A machining process is commonplace in most manufacturing settings. Now, the reason for this is it looks really smooth in this picture. However, it's generally not. Generally, you're going to have layers that go over each other and meld over each other. So you're going to have to use some subtractive manufacturing on this. They're often costly, usually because of the size of the machine. So these machines are huge. They're used like by aerospace companies or military grade companies to create PV parts, production value parts. A DED process can utilize a 5-axis machine for positioning. So like a FANUC arm, it will use a FANUC arm to do that welding. And then can be used for object repair as well as creation. So that's an interesting thing about DED, because when you go in, let's say you screw up a mold or something like that in industry, usually they weld it up so that they can create a nice surface for them to work on. This can be used to make those repairs. And generally, there will be post-processing to this. So there are hybrid machines that they will put a DED machine on where they have the powder feed and the laser melting it. And then there's the secondary post-processing built into that machine. So you'll actually buy a full mill and this, and that will cut down on your setup time. So moving forward, you have directed energy deposition, EBAM. So instead of using that laser, you're using an electron beam gun. So as the name entails, electron beam and in manufacturing. So it's really similar to how DED works. It's pretty much exactly the same, except for the EB gun. So it is a DED process. It uses an electron beam for faster melting. So that electron beam will get hotter than the normal lasers. And using that higher heat, your residual stresses in your print are going to be lessened. So essentially, you're heating it up so it doesn't crack or stress crack later on. So that would be one of the advantages of using EBAM instead of regular DED. And it utilizes a vacuum environment, so inert gases aren't needed. So generally in the DED process, it's like a welding process, right? If you were going to go home and weld something, you have to use inert gas on like a MIG gun. Now, with an EB gun, you don't want any gas in that chamber because it will disrupt that electron beam gun and cause it not to heat up as effectively, and you won't get the heating that actually puts that benefit to your residual stresses. So now that we know a little bit about DED, I'm going to switch it up on you because DED is mainly made for metals. This is going to be the powder bed fusion for polymer SLS. And the reason why I want to bring this up is because you're using that same powder that you would in a possible DED solution. Except instead of it spraying it and you're melting it as it sprays, you're taking your roller and then building up your layers of powder, layer by layer, and then melting it with a laser instead of spraying it directly onto the part or placing it directly onto the part in layers. So with the polymer version, the powder bed fusion process may not use supports, instead uses powder bed as the support, leading to smaller amounts of post-processing. So generally in DED and powder bed, you're not going to have the amount of supports that you would in other 3D printing. So if I pass this part around, this is an FDM part or FFF part. You're going to see that they have these tall walls, pillars that are built up to hold up the rest of the layers. So as you're going up, it has to hold the layers. So because of that, you have to do post-processing to get those supports off. SLS will create a better surface finish than Triple F. However, it's much more expensive. So these could range. I can't give you an exact price on them, but they are more expensive. They're probably over 10, yeah, probably over 30,000 at some points, which I will pass these two parts around so you can kind of tell the difference in surface finish. These are both powder bed fusion, the SLS. So generally it comes out pretty grainy, but depending on your particle size of that plastic that you're pushing on to your bed, it creates finer particles. Finer particles equal better surface finish. So moving on, of course, we have to have the metal versions, DMLS and SLM. So those are direct metal laser sintering or selective laser melting. So these are going to use, instead of powdered plastic, they're going to use powdered metals. So DLMS is going to use alloy powders like tool steels and aluminum alloys. And then SLM uses metals with heightened mechanical properties like titanium and stainless steel. And the reason why this is because the laser itself, there isn't as much of that laser going around in a DLMS process. So it's going to be a little bit cheaper. Both process are going to require an inert gas. So it's like that welding that we talked about in DED. We're basically melting this powder the same way we would be in a DED process with the powder nozzle. Like I mentioned before, SLM uses more high-powered lasers. So what that means is you can melt metals with heightened mechanical properties like titanium and stainless steel, like mentioned before. And of course, we have to have an electron beam version of this, just like DED. So this is electron beam melting. And similar process to SLM, difference include a vacuum chamber and electron beam. So it's the same concept as before. We're basically using an electron beam to melt instead of our laser. Like we said before, higher energy process, higher heat, better management over thermal stress, residual stresses are lessened. This kind of results in better dimensional accuracy than SLM. Because with the laser, you can end up with warping or differential cooling in your metals. But at the same time, since it is a hotter process, cooling time is going to be needed to be included in that. So moving forward from powder bed fusion, we're going to get into binder jetting. So the binder jetting process is very similar to the powder bed process, but a little bit different. Because rather than just using a bed with a roller where it comes up and pushes your material over and then shoots it with a laser, now you have another component right up here, which is your binder head. So basically, you're dropping this binder on the part where that powder layer is. So when you hit that powder layer, put the binder on there, you build up the next one, and that's what holds your powder together rather than a laser hitting it and melting it or centering it together. So right up here, like I said, like powder bed processes, however the binder creates the layer geometry. What's interesting about this before we go into here, we're going to talk about continuous and DOD, what that means. So up in the binder head, right here, it's basically how you're dropping your binder. So DOD is going to be right over here, and it's going to be controlled by pressure. So it holds up your binder, and whenever you want to drop it, it releases it through the use of pressure, holding it in. With continuous, it's a continuous flow. However, you're diverting that flow. So you have a little bit more control with your drop on demand on where it's at rather than your continuous. Since we know kind of how this works now, secondary operations such as sintering or infiltration may be needed for mechanical properties in the use of metal powders. So the thing with binder jetting is it just doesn't take place with a plastic powder. It could take place with a ceramic, it could take place with a polymer. Anything in this powdered form that the binder can be put on, it can create. So you can also use like wood or sand, which that brings us to the sintering or infiltration portion of the presentation. So basically the sintering portion, you can stick it in the oven, it'll sinter itself together, meld together, or you have the infiltration portion where you're actually using this portion and melting it out like you would in a dye. So I know you had asked a question earlier on if that's possible. This would be kind of where that would be. So that material that was shown earlier, I don't know who has it right now, but the powder, I'm looking for the other one. Yep, that one right there. So if everybody wants to turn around, that's the powder that would come out. So something of that nature. Moving forward off binder jetting, we have a completely different process, which is material jetting. So material jetting itself can either be DOD continuous. You're essentially dropping resin this time though, instead of your binder. So a photopolymer resin. So what this is going to do is it's going to lay the material directly in the bed as it's UV cured. So it layers layer by layer, layers it down, UV cures it, layers it down, UV cures it. So because you're not using a powder and rather you're using direct resin, you get high dimensional accuracy up to plus or minus a 0.1%. Multi-material and multicolored printing is available. So generally in 3D printing, you're going to use one color. The metals aren't going to change color either. But in this one, you can kind of take that liquid resin material that this is dropping and you can add colorant to it. So kind of like your printer at home, essentially. But now you're layering it up and curing it with UV. Downside of this, it uses a great amount of support material. So this part right here is a material jetting part that actually comes from, that's a prototype off of one of Hydra's parts. Now, as you can see on this part, as I pass it around, or as it gets passed around, that it's going to be smooth, but that whole part was encased in kind of a rubbery support material before it came off. Like I said before, it's got an excellent surface finish. It's smooth. Moving forward, we're going to get away from all this stuff, first of all. We're going to move on to something different. Get away from the powders, get away from, the jetting, and we're going to go to sheet lamination, LOM. So laminated object manufacturing. So with this one, you're basically taking a polymer coated paper and building up a block and then cutting that block out with either a laser or a blade. Now, the interesting thing about this is it's not technically an additive manufacturing process. There's additive manufacturing elements to it, but it's actually considered a subtractive process. So LOM may utilize either a blade or a laser. So right up here, what it's cutting with is that blade or a laser. LOM can create large prototypes for less cost than other 3D printing methods. So the reason why that is it's because of the material itself. So as that rolls over and it cuts it out layer by layer, all you're using is a paper with glue essentially. So it's not really a costly thing. An LOM process supports may not be needed, however, undercuts may be a challenge. Since you're cutting it out of this block. If you have something with a ledge on it that's an undercut and you try to pull it away from the part, you might have trouble doing that because it's not like a support material that you can break away. The actual paper itself feels like wood when it's all dried. Moving forward, LOM produced may have low dimensional accuracy and surface finish. So you're cutting it with a laser or a knife. So if the paper gets moved in any way, or if it wrinkles as it's printing, it's going to leave a bad surface finish on the part. And generally, it's not a great surface finish to begin with. I don't have one here today. It's a pretty rare breed of 3D printing to see out in the world today. So like I said before, LOM is considered a subtractive method of manufacturing, however, has qualities of additive manufacturing. So you're building up the layers. You're just building a block and then cutting out from the rest of it. But here's another type of sheet lamination called UAM. Now this one is more highly used ultrasonic additive manufacturing. Basically this one still builds up a block, but now you're machining said block on a mill, which is way more accurate. So it's a similar concept to LOM. The layers of metal tape are ultrasonically welded together and machined. So basically, instead of that paper with glue on it, now you're taking strips of metal and ultrasonically welding them together. Because of this, dissimilar metals may be used in this process. So if you had something on the outside of your part that you wanted to have a little bit more thermal conductivity, like a copper or something like that, you could melt or weld it to, let's say, an aluminum. And this has higher dimensional accuracy than LOM. So Basically, you have it on a machine. You have it on a mill. It's going to be a lot more accurate than just a knife and a laser trying to cut out paper. And it's metal too. So, moving on down the line, we have vat photopolymerization or vat polymerization, stereolithography, SLA. Now, this is one of the oldest processes out there to date. And what it does is it uses a laser to photochemically solidify polymers using a UV light. So it's a UV cure resin. It's a liquid. Basically what happens is the platform is dunked in this liquid resin and the laser comes over and cures that part. So shines the UV where it wants it to cure, layer by layer. So actually, I have a few parts out here today that if you want to pass them around. They are SLA printed. Now, those are actual prototypes that are used at Flowrite that they've been graciously good enough to let me use. So, moving forward with that, the part will not be fully cured after print. Post-process UV curing is necessary to achieve better mechanical properties. So basically, you're shooting it with the UV. However, it's not curing fully. It cures the shape, but it doesn't cure the whole part. So that's why in the next slide, you'll see how the process works or the post-processing process to get them to have better mechanical properties. So due to accuracy of laser and small layer height of resin, parts are extremely smooth and accurate. So as you're passing those parts around, just feel how smooth they are. I mean, they don't have that little coarse feel as if they were a powder bed, even though that's still a good surface finish. Most photopolymers used will be brittle and not UV stable. So that's another thing. If you look at the parts, you'll see that two of them are broken. And that's because it's a brittle break. So generally, they're not that great outside. And if you're going to use them as a functional prototype, they don't really have a lot of good ways of bending. However, this has been combated with, in recent years, I should say, of certain polymers coming out that have more of a rubbery characteristic to them. So these will require support material that may leave marks, which we'll see in the next slide. Generally, when you break off support material, it's going to leave a mark on the part. So that's kind of another thing when you go back and look at the powder bed stuff, that you might have a better surface finish because you don't have a witness mark on the part. And hollow parts may need escape holes for resin. So when you're doing this, you're essentially dipping it in the resin and then curing it, taking it out, dipping it again, layer by layer by layer. And that liquid resin, that platform moves a little bit farther in that liquid resin as it goes. So when you have this, you may have places where that resin gets trapped. So that's why you want to put holes in your part, or else you might get a phenomenon known as cupping, where you have that material trapped in there. And as it gets trapped, it pressurizes a little bit to that bed, which could allow these to come off the platform. So your part would come off the platform because it would be pushed out by that resin. There's another type of SLA out there, or vat photopolymerization, excuse me, which is digital light process. So this is basically SLA on steroids. Instead of a laser, DLP is going to use a digital light projector. So since it's a UV cure, rather than just shooting a laser at one point and then moving it around the machine, you're going to get way more if you just shine the whole layer onto where you want it to be. So basically what I'm saying is rather than it just creating a layer by one point at a time, this creates a full layer at a time. That's why it's considered faster than SLA. However, because it's curing a full layer at a time, DLP pixels may leave witness marks on the finished part. So basically what you're going to see is on the part itself, you'll just see a little burn spot, or where that layer to layer, it's not as resolved as a common SLA part. And actually, with these vat photopolymerization methods or vat polymerization methods, these are like the secondary favorite of a hobbyist. So I know a lot of hobbyists that use these SLAs. So SLA and DLP post-processing. So right here is the SLA process finished. Basically, you were dunking your part the entire time. As you can see, supports are needed in SLA. They're branching supports. So essentially, it's a line that comes up, branches over, and touches the part in a certain location to hold it up. They are then washed to get any extra resin off of them, because that's gross. You don't want that cured on your part. And then the SLA parts are UV cured. So that's what gives it that extra mechanical property. You're hitting it with that light, allowing it to actually cure the rest of the way. And this is actually how, I don't know where they are right now, but there were two parts that went around that were prototypes from Fluorite. And they kind of have this shape to them. That was how they were printed right there. This is right after the process I took these pictures. And finally, the hobbyist favorite, and the favorite that is used in industry a lot of times, material extrusion. So I'm going to pass this around to show how it can be used out in industry. This was a fixture that was printed for one of our prototypes by our manufacturing engineer at Fluorite. And actually the prototype part was 3D printed as well. I think that was an SLA part. So triple F stands for fused filament fabrication, or if you're a Stratasys, which is the company that makes a type of triple F 3D printer, they coined the phrase fused deposition modeling, FDM. Same exact thing. So FDM and triple F are the same process, like we just went over. Triple F may have two extruders for alternate support or model materials. So you can have two different color model materials because you have your polymer here. It's essentially just a wire fed thing. The spool takes the wire into the extruder. you have a heated nozzle that pushes it out, and layer by layer, it goes around and prints the part. So it layers that wire fed material layer by layer. So sometimes, like you're seeing on this part right up here that was passed around, you could have a support material that might be water soluble or something easier to break off than what's currently on here. Or if I wanted two different colors on this, that's how I would do it. Some objects will require supports and a secondary operation to remove them. So again, like we see on the part that I just held up, it has these supports that hold up the layers as it goes along. And printers can be enclosed or opened based on material specification and processing needs. So basically, certain polymers you don't need an enclosure for. So when I say enclosure, I mean you're basically taking your heated bed here, all of this, and putting it into an enclosed space to keep the temperature where you want it. So you don't have those rapid temperature changes. So when we actually go into creating these parts, there's a couple things that we have to do before printing on any type of 3D printing process. So now that we've been through them all, I can kind of start going into this in terms of using the example of triple F. Some of these will be the same for all 3D printing, some won't. Some will just adhere to the triple F. Because as of right now, that's kind of the most widely used type of 3D printing, as well as it's what a lot of hobbyists use. So if you guys were to go out today and look at 3D printers, that's probably what you'd be looking for in the cost range. So part design and print orientation can make a difference in additive manufacturing. So basically, when you start slicing, you first start off with a model. Create your model in CAD software such as SolidWorks or Creo, and you then put it in a slicer. So what that slicer is going to do is it's going to take that part and cut it layer by layer by layer by layer and create your tool path. So what your extruder or your wire feed follows on, or what laser follows that path. It's going to create the path for that to follow. So part design and print orientation, like I said, make a difference. So if I'm going to do something like I did here with this, I'm not going to put it on one corner sitting on the bed in the printer, right? Because then I need support material to hold up this layer. I need support material to hold up over here. It's just a waste and it won't look nice. It won't have the mechanical properties I want. Speaking of mechanical properties, parts will have diminished mechanical properties in the Z direction rather than the X and Y due to layering and molecular orientation. So this doesn't really take place in powder beds, but it does take place in extrusion. So holding up this part, if you guys saw, you got this big line right here. Now that line, because I'm layering it layer by layer, it's got to meld together on that line. So you're essentially creating a weak point in that Z direction. So it's easier to tear apart in that Z direction. However, because the extruder is going in the X and Y direction, around and around and around, the molecular orientation of the polymer is going to line up in that direction. So all these little chains are going to line up, hold close together in that direction, and make it harder to tear that part apart or break that part in that direction. Part orientation will determine support needs. Just went over that. You're not going to put a corner, you know, set it up in a corner like this and have all that support material on top of there. Doesn't make any sense. General rule of thumb is 45-degree angle or more for vertical wall will need supports. So I don't know why. I'm just going to keep picking up this part. So these cutouts right here, they're at 90 degree to my vertical wall. So that's why they need supports. They need something to hold it up. So when you get over that 45-degree mark, you're going to need something to hold up the rest of that layer. We just talked about this, how they will be first designed in a 3D modeling software and saved as an STL. Maybe not the STL part. So an STL file basically breaks up your CAD model into layers so that Slicer can read it and create your tool path. Because like we said at the very, very beginning of this presentation, that it's based on building a part up layer by layer by layer with that material. Part STL is placed in the slicer where the toolpath and parameters for the print created, and then is sent out as a different file type for the printer to read. So like I went into before, you put it in that slicer and it takes that toolpath layer, but when it's in that slicer, you can set the parameters. So like the heat of your nozzle, the heat of your bed that your print would sit on, the intensity of your laser, if you're using powder bed, and what material you're using. So since we mentioned parameters, here are some for triple F printer. So material, obviously it sets the material to be printed. So if you want an ABS or if you want something weird like a nylon, you can set that printer to do that. Layer height. Now layer height is the next thing, and it's very big in triple F 3D printing. It's where that's right here. This part right here, that layer, how tall it is, how much interference it has. So more layers is going to allow the part to be more resolute. It's going to look nicer. You know, you're not going to have like big spaces or gaps in between those layers that you create. However, it takes more time to print more layers, more material too. Shells, solid layers on the outside of the part. So what's interesting about triple F 3D printing is if I broke this, the inside's going to be hollow. Or it could be hollow. So basically there's a pattern printed on the inside to hold up the part. And the shells are the solid layer on the outside that make up the finished surface. Infill pattern. It selects the pattern on the inside of the part. So if you were to break apart this part again, you'll probably see like a honeycomb pattern in here. What that does is different infill patterns can create different properties in the parts. So let's say I had something where I wanted to pull in this direction. Try not to pull it apart. I would print it in the infill in straight lines so that it didn't want to pull apart. Or if I wanted overall strength in my part, I'd print in either triangle or honeycombs. If I wanted the part to be lightweight, I could change it to like a concentric, where it would print like one circle in the middle, one circle in the outside, and then on and on and on, just like this, to kind of create that target effect. You can also do it in squares as well. Infill density, the amount of infill in the part. So how much are you actually going to put in the part? So you can have 50% infill, so you're filling it up 50%, that hollow area, or you can have, I don't know, 100% where it's fully filled. Usually rule of thumb states that it's 15. That should give you good enough mechanical properties for a prototype. Support. Name and tails as support to the part. Skirts, rims, and rafts. So when this is created, it has a heated bed that it sits on and adheres to. These help create a base layer adhesion to that, so it doesn't come off while it's printing. And that's where most triple F 3D prints fail, is it'll come off the printer, it'll move around, and it can't follow that tool path anymore. So when that happens, it ends up being a struggle, because now you have your part flown off, materials, printed already all over the place. So these help combat that. So skirts, what they're going to do is they're just going to create a square on the part, or a shape around the part. And what that does is it primes the nozzle and gets the material ready. That is actually supposed to say brims, but I had a mistype there. Brims are going to be connected to the part. So it's going to do the same thing. It's going to go around the part, but this time it's connected to the part, and it gives it more surface area to stick to that bed. And rafts are going to create a large surface area underneath the part. It's built up just like a raft out on the ocean that your part sits on. And it makes it where it sticks directly to that bed. Downside of rafts, though, coming from personal experience, they are hard to get off your part. So they will stick to your part like they were a part of your part. Cooling controls cooling fans. So you control the temperature in that space so that it doesn't warp, because that's the differential of temperature in your part. So if you can control around that part and around where you're printing at your nozzle head, you control if it's going to warp or not. Extruder temperature controls extruder heat. So that's going to control the viscosity of your material coming out of your nozzle. Bed temperature controls the heated bed temperature. Another obvious thing, but when you have that heated bed, the hotter you get it, that polymer wants to adhere to it. So it's what makes it stick there and allows you to build up from that first layer. So in triple F, that first layer is extremely important, as well as most 3D printing applications. I mean, it's the base for your whole entire part. So controlling that heat at the bed allows you to complete your part. So it doesn't come off or move around, which actually can be seen on this one. If we look very closely, it's starting to come off the bed. And that's what creates that warping, that U space, or that U shape on the very bottom of the part. Finally, acceleration and speeds. So 3D printer, it's a 3-axis machine. It goes X, Y, and Z. That's going to control how fast you move towards the spot and how fast it ramps up towards that spot in your tool path. Basically, with the acceleration and speeds, the faster you go, the faster you can get your print off your printer. Slower you go, the nicer it's going to look. Moving forward, you can assign these in your slicer. You're going to assign your materials. So just some basic materials, because they can have a vast array of different support and model materials with many different colors, mechanical properties, and processing specifications. These are some basics. So PLA, very easy to print. If you go buy a printer off the shelf and get material for it, PLA is the one to get. You don't have to encase it. You don't have to enclose it. It's friendly. It's like, coming from an injection molding standpoint, how everybody says, oh, well, HDPE or high density polyethylene is very easy to do. PLA is the high density polyethylene of the 3D printing world. So you get different variations for mechanical properties. So an example of this would be if you went out to, there's a 3D printing company out there called Raise 3D. If you went out and bought their PLA Plus, it's going to have heightened mechanical properties instead of just the regular PLA that you would buy. It's biodegradable. So PLA stands for polylactic acid. So it's not necessarily intended for long-term use. So if you go and give this to somebody and they stick it out in the UV and outdoors, it's going to break down. It's not going to last a lifetime. Does not need an enclosure for printing, which is a huge positive. You just go and print it. It doesn't necessarily, it isn't prone to warping. It doesn't want to really warp off the bed as easy as the other two materials I have listed here. So it makes it really, really easy to print. And it is a lower cost point, which is really nice, because then you're not spending a ton of money on something that you don't need the mechanical properties for. Next one is PETG, polyethylene terephthalate glycol. I'm sorry. It's more expensive on average than PLA. It's got better impact resistance and flexibility than PLA. So basically, if you want a heightened mechanical property in your part to PLA, this would be the next thing to go to. Better UV resistance than PLA. That's basically all of them. Better tensile strength than PLA and ABS. It's easier to print than ABS and harder than PLA. And enclosures are recommended. So basically this stuff, if you're not careful with how you utilize it, it will warp off that bed. If you're not careful with your heat or if there is a draft coming through that window, or, you know, you have a fan on it on the other side of the room, that differential cooling in the part, it's going to really want to warp off the bed, converse to PLA that isn't going to be as prone to warping. Then there's ABS, which is more expensive on average than PLA, slightly lower than PETG. So PETG and acrylonitrile butadiene styrene are going to be just about the same level in cost. It's got better impact resistance and flexibility than PLA. Both of these will have that, but slightly lower than PETG. It's going to have a higher heat resistance than PETG. That's why people like it. That's one of the main reasons that people would use this over PETG. That and excellent post-processing characteristics. So you can go on this if you really wanted to, you can machine it. And then there's also a trick with some acetone, where you just take acetone, it'll break down the ABS and create a smooth surface finish. So instead of having layers like this, you can take acetone, wipe it on quickly, wipe it off quickly, and it'll create a smooth surface finish to it because it breaks down the top of those layers. Again, enclosure is recommended. I'm going to say that it's more than highly recommended. It's almost, unless you have something very small that you know you have under control, you're going to want an enclosure for this. It will warp. It will warp. That's coming from experience. Actually, speaking of that, this is ABS. So where it's starting to warp, this was even an enclosed printer. So moving forward, if you do end up getting a 3D printer, I just wanted to give you guys some troubleshooting tips. So for general troubleshooting, use a 5-way approach to find the root of the problem. So basically, go down that path of asking yourself, you know, why did this happen? I don't know if you guys fully know a 5-way approach, but it's definitely something to go in and research. It's a pretty simple process. But I'm not going to go through that today. I'm just going to list some common issues. So common issues, bed adhesion problems. Leveling print bed is going to be your first solution. Basically, if you have a print bed that's like this, and your tool path is layering on perpendicular to that, obviously you're going to have a little bit of a problem. Your stuff is going to be cocked in a weird way that isn't necessarily correct. And it's going to want to warp off that bed. Cleaning the print bed. So when we take stuff off 3D printers of any type, our fingers have oil on them. So where those spots are that you pick up the part or touch that bed, it's going to leave a layer of film that prevents adhesion to that bed. Correct bed and material temperature. If you got the bed too cold, it's not going to want to stick to the bed. Plain and simple. Adjust to a higher bed temperature to improve adhesion. So you get a little bit more movement in your polymer. It's going to want to grasp onto that bed. And using a textured adhesion plate or glue stick for initial layer. So when I printed this, it was at the bottom here. Well, I didn't print it, but manufacturing guy did. He printed it with it sitting on the bed right here. Now, what a glue stick is gonna do is it's an adhesive. It's gonna stick it to the bed. It's meant for the initial layer. The other part, a texture adhesion plate, is gonna create more surface area for your polymer to grab onto to stick to that bed and hold onto it. Another common issue is filament jams. So some common solutions for that one. Check filament to see if it is aged or wet. So if you have a roll of material sitting for a very long time and it gets wet or it absorbs moisture, it might degrade in the nozzle. It might break off in the nozzle because it gets brittle. So trying to do some preventive maintenance there. Check filament tubes for blockages. So on a 3D printer, when of the extrusion type, generally they have tubes that hold that material that's spooled up. And if those filament tubes get blocked, then you can't really get the filament material to the extruder itself. So when that gets blocked and you don't clear them, you're not going to get it to the nozzle. Check for snags and filament spool. So I have to admit, this has gotten me before. You're rolling it off a spool of material. Sometimes, if it's rolled up incorrectly from the manufacturer, it can get crossed over, and that tension on the material is going to hold it to the spool and not allow it to feed into your extruder. And generally, this is a pretty easy one to check for, and sometimes people miss it. Common issues, filament jams, common solution. Or I'm sorry, not filament jams. That's supposed to say warping. I apologize. So use of a brim to keep parts secured to the bed. So those platform additions, such as your skirt, your brim, and your raft, are gonna keep it glued down. Like we talked about before. Avoid drafts for even part cooling. So generally for even part cooling, if one side's cooler than the other, it's going to shrink at a different rate away from the bed. So that causes that bed warping. So that's why you would want an enclosed printer. And again, like we've said before, adjust to a higher bed temperature to improve adhesion. So, because we've talked so much about triple F 3D printing, and that's going to be the start point for a lot of companies, and as well as a lot of hobbyists, when quoting or purchasing of any additive manufacturing machine, consider the following. So this mostly applies to triple F printers, but it also goes into applying to every 3D printer that you could ever quote. Part requirements. So if I have a metal part, I'm not going to go out and buy a polymer bed, SLS 3D printer or triple F 3D printer that's going to print plastic. Or if I want a smooth surface finish, I'm not going to go buy a triple F 3D printer. I'm going to go buy an SLA 3D printer. So it's basically your part requirements that you really have to think about. Another good example actually is EBAM versus DED. If your part has problems with stresses or residual stress left in that part, or is going to be prone to cracking, and you know that, when you go into it, you would buy an EBAM machine instead of just a regular DED machine, like we talked about in the first part of the presentation. Material capabilities. This counts for triple F printing and everyone of them out there. Because if I'm going to go buy an SLM printer for only aluminum, I'm wasting my money. I would go buy a DMLES printer because it doesn't have the more powerful lasers in it. I don't need as much heat. If I'm going to print ABS and I know I'm going to print ABS, I'm not going to go out and buy an unenclosed printer. I'm going to buy one that's enclosed so that I don't get that differential cooling. Process speed. The faster your printer goes, it's gonna cost a little bit more. You might be able to get some different printers out there that print faster and accurately for cheaper. It's just shopping around for them. Process quality. If I want a nice looking part, I'm not going to go out and buy an LOM printer that's notorious for having low dimensional accuracy and low surface finish quality. I'm going to go buy something that would be akin to like a material jetting that has a nice smooth surface. Process requirements. I mean, if I'm going to use titanium, I'm going to buy an SLM printer instead of a DLMS. I need the hotter heat. Print area, you pay for print area. One good example of this is I was working at my previous employer. I went out and we started quoting 3D printers. And one of the big things is we had a bigger part with, you know, a larger footprint. We had trouble finding a 3D printer for the job under $1,000. We ended up having to buy a printer for $8,000 just for the size of the part. So you pay for print area, machine reliability and maintenance. Buy a machine that you don't have to do maintenance on daily. You will eventually have to do maintenance on them. Stuff breaks, you know, there's wear items on these. But if I was going to go buy a, you know, triple F printer versus a material jet printer or a material jetting printer, the material jetting is probably going to last longer. It's going to be a little bit better built. I'm not going to have to worry as much about it. It's the same if I bought a $60,000 printer for FDM compared to like $100 printer. You're going to have to do more maintenance on the, well, I shouldn't say 100, the $300 printer. And that's, I mean, it's how much work you really want to put into it. Machine features. This is kind of a cool one. So if I'm going to buy a cheap FDM printer, it's going to require me to level that bed manually. So if I have it like this, shift it over this way, I have to manually go underneath it and then push it up like this. So there are 3D printers out there that have auto bed leveling features so that you don't have to worry about that. And finally, money talks, cost. So how much are you willing realistically to pay for a 3D printer? So I am not going to go buy a DED machine, which you have to get quoted because you're going to get sticker shock. So they don't even put the price tag on a lot of them. versus I can go online right now and buy a 3D printer for around $300, if I remember correctly. So finally, recommendations for printers. One would want to start printing triple F, which is kind of the hobbyist gold standard right now, other than SLA. Is an affordable way to begin printing models for basic fixture prototypes and objects. Here's some recommendations. So you guys have seen fixtures, prototypes, and various objects that have been passed around the room, those who are here in person. Two recommendations for just triple F 3D printers, Ender 3 series. So if you go to Creality's website, I think these ones are around $300 or something like that. And there's different models that you can get. It's not enclosed, but you can buy enclosures for them. If you ever wanted to start, just get something quick and dirty. Do you have one up right now in the back? How much does it cost? Okay. Yeah. So pretty low cost for a printer. And then Bamboo Lab. This one's a little bit more expensive, but it's a workhorse. That's actually what this was printed on. Moving forward, some recommendations in case you guys want to start a journey. Beginner's tools. I wish I knew these things when I first started out. Get putty knives to get it off the bed. Great for material and removal and bed cleaning. Isopropyl alcohol. Recently, I talked about how our fingers have oils on them that get left on the bed that prevent adhesion. Isopropyl alcohol is the way to get it off. So you just go over, wipe it, it dries. Well, it's bed adhesion. 0.04 millimeter needles and tweezers. These are good for cleaning out your nozzle tips. So when you're extruding the material through, your gear pump grabs it, pushes it through that heated nozzle. This pushes out any material that's left out of there. And this is just great for getting material jams out. I've used these before. Hooks and picks. If you guys look here, you can see some of the support material has been taken off. That's what I used to get that off. So this is the end of the presentation. I kind of gave you guys a little bit of a what's out there and what you guys can receive. Are there any questions for me on some of the processes that we covered? 1, 2, 3. Okay.
Let me go back to the very basics. The industrial prototype making is what you're talking about, not production. You're not making parts to sell. You're making prototypes of parts you're manufacturing in the rest of the factory, correct?
That is actually dependent. Most of these, such as binder jetting, material jetting, well, I shouldn't say binder jetting. Material jetting, SLA, and triple F, as well as like LOM, are used for just prototyping, but some of these can actually be used out in actual manufacturing for production value parts. So like DED, what they would do is they would print off the model itself and then they would go back and machine it for like one-offs or custom stuff.
The other thing I wondered about, you mentioned hobbyists, and $300 for a hobbyist. There's also gotta be software of some sort, even for a hobbyist to make anything. Is that not correct?
That is correct. Generally, the software is free, so you can actually get on Creality's website where you get the Ender 3, and then you would download the software. Actually, while I was doing this presentation for a reference, for the important parameters that we went through, I downloaded Raise 3D's slicer to go over the parameters and put a part in and actually slice it up.
Okay, when you read about weapons being made on a 3D printer, functioning weapons, pistols, for example, what
I knew this question was coming.
what kinds of materials would need to be made to have a functioning pistol? Presumably on the most high-end 3D printer.
I've seen hobbyists do them. I have,
Out of materials similar to what you passed around?
I would say that it's a possibility, yes. Depending on the material, a lot of it's gonna depend on heat and mechanical properties to do something like that.
But generally metallic materials, correct?
No,
No,
no, you can do it with polymer materials.
polymer materials.
Yep, there are high heat polymers out there that are capable of doing that.
Okay. And the most high-end printer or not necessarily?
Not necessarily.
Okay.
I've seen people do it on FDM printers,
Wow.
believe it or not,
Okay.
depending on how high heat that goes.
Okay, thank you.
Yep.
You talked about many of the polymers at the end, but earlier on you talked about powders, but you didn't describe them. So what chemicals are used in those powders? That's the first question. The second one is relating to the lasers that are used. Is there a preferred range of wavelengths for those lasers to actually perform that function?
So in terms of the polymers, it's powdered polymer. So generally you could end up getting like a nylon or an ABS or something like that. Sometimes you can go from engineering to like lower end polymers, if you will. It's just powdered polymer. So they just take it and put it in a powdered form. And for the lasers, that I can't really answer for you on that end. In terms of the wavelengths of the lasers, I don't know for certain.
Another question for materials. In recent years, I've been very interested in what the people in the field call bioprinting, and they use what they call bioinks to create materials that would be used for body parts. Today, a lot of dental laboratories make tooth implants with 3D printing. What material is used for that purpose?
For
To make a
Mm.
tooth, a facsimile of a tooth that will be implanted in a patient.
that, I don't know offhand. It'd probably be some type of thermoset would generally be what would be used.
Thank you.
Good questions.
Just one question that I had was, you said that you'd have a laser beam and then you'd have an electron beam,
Yep.
but the electron beam had higher energy,
Yep.
but it caused less heat, less distortion. Why would that be? You're putting more energy into a part?
Yeah. Well, the cooling time, you're able to control that temperature a little bit better with your cooling rather than if you were to heat up just one end with a laser and it cooled quickly on the other end, you're able to keep more heat in that part, lowering your delta T.
Question here.
Yep.
I worked in the medical device industry for 25 years, and we had a heart valve that was CNC milled from titanium.
Yep.
I know it's a subtractive process, but is there anything equivalent today for the very close tolerances you would need between the aperture and the housing with this type of process?
Yep. So if there was anything close, it would probably be a DED, EBAM, or powder bed process. And the reason for that is because you're gonna get your post process machining in there as well. So it's not necessarily you are printing the entire part, but you're actually going in and finishing that post process. So you would go in with the CNC as a secondary operation, but you would be saving all the material that you would have to cut out.
Because there's so much waste. I remember taking some heart surgeons in to see how we made these heart valves, and they're going, "What do you do with the rest of that titanium?" I said, "We make airplanes out of them, you know, obviously."
Yeah, we can melt it down again. It's
Yeah.
fine.
Sell it to Boeing.
Which actually, I think Boeing uses some of that DED technology.
At the beginning of your presentation, you talked about 5 axes. And then later on, you showed the X, Y, and Z. What are the other 2?
The other 2 axes.
Yeah, you said 5 axes.
Yeah, so generally you're moving in your X, Y, and Z for 3, and then A and B are rotational.
Rotational, how does that work?
Look behind you. He's got you. Yeah, you're swinging on it. Yep. Yep, so you're not just having one point. If you ever seen a FANUC arm work, that would be kind of what you would be looking for.
One more question there.
Real novice question. For the hobbyist, what about CAD?
CAD?
Telling the printer what to print. What are the options for that? I didn't see that on Amazon.
Oh, so actually I would go to SolidWorks. They have a hobbyist license. I have my at-work license as well as a hobbyist license at home. Generally, when you go and get that, you can get like SolidWorks for really cheap because they have certain packages for hobbyists. You go to salt.com or solidworks.com, I forget what it is. But once you have that, you can actually, when you get your printer off the same website that you looked at your printer on, they should have a slicing software option that you can go in and download for free. That was actually what I was going to tell you too, that most of them are free.
Anything else? One more there.
This is probably crazy, but can you make a copy of something? Can you make a copy? Like, can you scan an object and then do it? That's what I want to do.
Yes, you can. There are 3D scanners out there.
Uh,
One of the companies out there, Keyence, makes one. There are hand scanners out there. So what they'll do is they'll take a point cloud, create a surface from that point cloud, and then go ahead and print that. Yes. Yes, you'd have to pay extra for the scanner though, and those are a little expensive.
What kind of things do hobbyists print 3D?
Whatever you want to print.
Yeah,
I
but
mean,
what? I saw some toys in here.
Yep.
But there have to be some other uses. A lot of people wouldn't make toys, right? What do
so
you make?
actually, this originally was a shadow box for my girlfriend, Jane. Where you would put a candle in it or some type of light source in it and it would shine out. So cool little objects like that. You can create different parts if you really wanted to get into this. Like I know my previous boss, He is from Holland and he has done golf carts. He does custom golf carts. And he has done 3D printed parts on those golf carts for his own personal use, obviously, but where if he needed a switch face or anything like that, or a housing, he would print those parts and then just screw them on. He's also done it on his Corvette for custom parts. Yep. Well, it's mostly custom interior parts. Yep. Okay, one more question.
Yeah, we've talked about the medical application of 3D printing. What other kinds of things can 3D printing do better than previous manufacturing processes could?
So if we go into anything custom, you know, if it's a custom metal part, or if you have something custom that you just want to print at home, that's a one-off that doesn't necessarily require a mold where you're making thousands of parts, but rather a really, really low volume. It works extremely well for that in a manufacturing setting. So maybe like even in the marine industry, you had, or military applications where you had only a couple of parts, you would be able to not have to pay a whole bunch of money and make those custom parts or make a custom mold for that, but you could 3D print those parts. So generally like in aircrafts, I've seen videos of this stuff being used like DED or EBAM. Sometimes custom car parts can be used, like I was saying, or if you wanted like a custom emblem, you could use 3D printing for that and then do some post-processing to it. Yeah. Well, you can use 3D printing for both prototyping and depending on how much you want to spend, which I mean, if you're a large Fortune 500 company and you buy a really nice 3D printer that's able to print metal and you can post-process it, you can make PB parts with that. And I mean, sometimes even if it's not necessarily the greatest thing in the world, and it's just a cheap part, you can also do that as well. Because I do know that for some designed plugs in displays that were throwaway parts that were very low volume, at the company I previously worked for, they would actually 3D print those. And those were for transport purposes.
Any other questions? Well, Jared, thank you.
Thank you.
If I thought 3D printing was not complicated, I know different now.